Can you see it in full screen now, Maud?
Yes.
Okay, so as Alessandro was saying, both Sofia and myself will give some will show some case studies. However, in my part, I will give also some theoretical background, let's say, because the focus of this presentation will be on the subsurface characterization using seismic noise, but in two different ways, let's say. In a first case, like designing a network, a seismic network, monitoring network, and so avoiding seismic noise can degrade the signal, and to let's say cover the small earthquakes. But on the other hand, we can use the ambient seismic noise to build subsurface velocity models using the interferometric method. So I'll show both of these methodologies, and then Sofia, as Alessandro was saying, will show a case study in China. So the main focus will be on noise, and you already had a brief introduction of by Professor Barone in the past about seismic interferometry and seismic noise in general. But I will give a very brief introduction on these topics that I will use later on in this presentation. So essentially, ambient noise, seismic ambient noise, can come from different sources. In this case, the natural sources that usually have very low frequencies and can be divided in different types, basically on different frequency bands. So we have the hum, which is the interaction of ocean waves with seafloor, which has very, very long periods, so very low frequencies. And then we have the two primary and secondary microseisms, which is basically the interaction of seismic waves, but near the coastline as a primary microseism. And the secondary microseism is the interaction of two different propagation waves, which pushes the seabed and creating some waves which propagate all around the globe. And these are the main waves, basically, that are employed to characterize the subsurface velocity models, especially the shear velocity models, at bigger scale, so a global scale, or a smaller scale, as our cases, at reservoir depth. But we have also some anthropogenic sources. Sometimes they are called cultural noise, which are basically produced by all human activities, wind farms in industries, trains and road traffic, and so on. And depending on our, let's say, interest in resolving global scale problems or local scale problems, we need to care about the noise and to characterize, especially to characterize noise. And as I was saying, the different sources of noise have also different frequencies, and the natural sources. So we start from hum, which is 100 seconds, so 1/100 hertz, up to roughly 1 hertz, while the anthropogenic sources are higher frequency signals, and we are interested in a frequency band between 1 hertz to 30-40 hertz. So we are in this in these frequency bands to be characterized. And as I said, the noise itself, as the word says, it's something that is unwanted. So basically, it's an interference that obscures the seismic events that we want to characterize. So, for example, characterize earthquakes or inactive source surveys. So we want to remove it. However, as I said, we can exploit the noise in using the seismic interferometry. And as I was just citing Curtis in 2006 was saying, turning noise into useful data and everything geophysicists dream, and now it seems possible. So this was a seminal paper on seismic interferometry back 20 years ago, roughly. So basically, they proved, but starting from the 60s, basically, but they proved that in these seminal papers that we can estimate the shear wave velocity of the subsurface by only looking at and listening to the seismic noise. However, in this first part, I will focus on the removing part. So we want to focus on the part that we want to avoid noise to better characterize seismic events and that we are interested in. As Alessandro was saying, for example, human activities in subsurface can induce strong earthquakes up to 5.5 magnitude units, which can be felt from the population. So it can be also dangerous for the population. So the aim of this will be the design of some seismic networks that can be useful to characterize and to detect these events. So why is it useful? As I was saying, the ability to detect and localize seismic events, so the earthquake that we are interested in, and we want to also reduce the localization uncertainty. So with this seismic network design, we want to essentially choose the best location, the best placements of seismic stations on the surface or in borehole to better characterize and to be ready to characterize seismic events. And this is crucial for earthquake early warning systems. That I won't talk about this in this lecture, but it's very, very important that in case of strong earthquake that can be launched like a warning system to inform the population. However, a good network, so a good geometry, improves also the estimation of some mechanical properties of the earthquake, which are very important also for us. So, for example, the focal mechanism, the fault orientation, and so on. And then we can use this information to better characterize the velocity or the other properties of rock volumes. And in our case, we want to monitor the subsurface human activities. And as I said, in many human activities can induce earthquakes. Also geothermal energy production, the carbon storage, the gas storage, and then as Sofia later on will show an example of EGS, which is an enhanced geothermal system, basically can induce very strong earthquakes. So in general, the seismic network design can be applied to a bigger scale, so for example, a country or in Europe or Italian network seismic stations. But in this case, we are focusing on the local seismic network, so on a small scale. So the design of a seismic network is basically we have some inputs. So in this case that we see in these arrows, and some velocity models of the subsurface. And we want to minimize the location uncertainty by placing the station on the surface and maximize the sensitivity of the network. And this is called as building up an optimum network geometry. So we want to do these things. But starting from the inputs, so what we have is first of all, the noise characterization, which is the main part. As I said, in this case, we want to reduce the noise because it interferes with the recordings. And so basically what we do is usually in a lucky case like this in France, we had like a very huge temporary networks of roughly 400 stations deployed in these areas. And basically what we do is for each of these sensor, we estimate the noise, so the characteristics of noise. And we usually do using the probability power spectral density, or PPSD. Essentially, PPSD is a measure of the amplitude distribution of noise that we see on the right-hand side, and essentially is a probability density function. So it's a distribution which the color indicates the probability. So where the color is red or bluish is as higher probability to have that amplitude at that frequency. And these are two cases, two different stations in these temporary networks, where we have very different characteristics. So in the first case, we have, as we see, the higher amplitude at so from 1 Hz to 100 Hz, while in this second case is much lower. And you already understand that the second case is the optimum, let's say, position to deploy a station because the seismic noise is very low. And these two lines are the reference curves, which basically we can compare the noise distribution with the low and the high level of noise. So closer to the higher curve, which indicates the noise is quite high, as we see on top, and the bottom represents the low limit of the noise. But if we measure these PPSDs for each of these sensors, and we interpolate the results for different frequency bands, we are able to build up some noise maps, which are the key in the design of a network, monitoring network. And basically what we see here is the noise maps builds up from the PPSDs in these two areas. And we see how is a little bit of a zoom on this. So each of these circles represent a station, and of course is interpolated throughout the area. But if we zoom in this second, we see that basically the color indicates the amplitude. So the yellow color indicates higher amplitude of noise, which is very coherent with the cities and roads, or there are some industries up here. So in this case, the color helps us, or these maps helps us to deploy, or to we can use as like a guide to place the seismic stations. So first of all, what we do is having characterize the noise. We want to have as output some metrics. So we have the azimuthal gap map, the sensitivity of network in map, and the location uncertainty. So we look at the azimuthal gap, which is basically is a measure of how well an event is surrounded by stations. And essentially, if we already know the target depth and so we can and the area where the operation will be done, we can set some stations and to calculate these maps in order to, as a first order of, let's say, so we can estimate how well the probability of to have some induced events to be surrounded by stations, and this is helpful to be characterized in a correct way. So both in as a location uncertainty and to estimate the magnitude and so on. The second matrix will be the location uncertainty, which is related to the azimuthal gap. So we have, if we are outside the seismic network, so where the azimuthal gap is above 180 degrees, with the location uncertainty will be much higher than within the seismic network. So we look at how we can build these location uncertainty maps through the several calculations that I will show in these slides. So the location uncertainty is basically as a function of two different types of errors. The first one will be related to how we are able to pick correctly the first arrival of an event. So basically, if the noise is quite strong, we are not able to pick correctly the first onset of P and S waves. So the uncertainty will be higher. If the noise is quite low, as the figure on top, we are able to pick correctly the first arrival. So in that case, we are able to have lower uncertainty on the peaks. But we can do this analytically. So there are some analytical equations that we employ to estimate the distribution of these errors. And we do that using this equation, which is related to the signal to noise ratio of the signal trace. And of course, the higher the noise, the worse will be the signal to noise ratio, larger will be the uncertainty. So in this case, but we are simulating the uncertainty. So we can set some thresholds of signal to noise ratio, and we simulate how this basically produces the differences in location uncertainty. And of course, a better seismic station location, lower uncertainties. A second location uncertainty, so a second source of error in the location uncertainty is the travel time uncertainty, which is related to the velocity model uncertainty. So we don't know exactly the structure of the subsurface, nor the exact velocity models. So what we can do is to have some velocity models and perturb those velocity models with some homogeneous with some perturbation, and we can simulate how this perturbation influence the final location uncertainty. So in the ideal case, if we want to localize an event, if we know exactly the velocity models and we have a noise-free data, the event is basically can be localized by just the triangulation or the circle method, where the intersection of these circles with a radius of a differential time between S and P is given. So as we see here, the intersection of these circles gives us the location of an event. So in this case, in 2 dimensions, but this can be done in 3 dimensions as well. And the intersection of these circles represent the optimum location of the event. But if we consider the errors, so both the errors in the travel time and the peaking errors, we don't have only one point of intersection, but we have a surface in this case, but a volume. So if we know the velocity models, we can estimate this volume through numerical models. And I show you some 2 examples of this, where we have a monitor network here with several stations, and we can simulate the volume of localization volume of a theoretical event in this on the northeast. You see my pointer? Yes. On top of here. So we see that this is the volume of all the intersections of the spherical shells intersect. So this volume represents the basically the where the potential hypocenters could be. But in this case, we are not interested in locating an event, but we want to estimate the error associated to this localization. And this can be done using some statistical measures of standard deviation, mean, median, and so on of this volume. But if we look at another hypothetical event within the stations, monitoring network stations, we see that the volume, the localization volume, is much smaller than before. And as I said already, anticipated before, the azimuthal gap in this case is a first order approximation of the localization errors, because we are within the stations, the networks, and the localization volume is much smaller. So this, again, we can, within this volume, we can build the distribution of the RMS errors in travel time. And from here, we can estimate the errors, both vertical and horizontal, using for example, the standard deviation. And again, as we compare with the 2 cases, we see that within the network, the error is much lower. And if we do that for different hypothetical hypocenters in a 3D grid using the same network stations on the surface, we can build up some maps that tells us where we have the high uncertainties in both vertical and horizontal, in both in depth slice, or in vertical slices. So here we see just 2 depth slices for vertical and horizontal uncertainty maps. So what we do here is, so this is done for one single network, surface network. So because we want to optimize this, we can move around in different ways, either in trial and error, let's say, methodology, or in a more complete and like in more statistical approach. We can move around the stations in order to optimize and to minimize these uncertainties in the area that we are interested in. And finally, we look at how we can build the same maps for the sensitivity of a network. Sensitivity of a network means that, so we want to answer the question, what is the minimum magnitude that an earthquake can be detected by the stations at the surface? And of course, here again, there is the key aspect of the ambient noise, because the higher the noise, lower will be our way to detect an event. So what we do here is to simulate again on theoretical hypocenters, which is the response at the receiver location. In this case, the source spectrum at the receiver location using the Bruns model, which is this here on the bottom. And this depends on different parameters, but of course is important the distance from the receiver and some characteristics of velocity models and the frequency and so on. And of course, the magnitude of the earthquake itself. So the higher the amplitude or the magnitude, higher will be let's say the signal which arrives to the receivers. And again, if we do that for different receivers at the surface and for different theoretical hypothetical hypocenters in different depths, we can compute the theoretical response for each of these hypothetical earthquake to the stations on the surface, and we can build up we can compute the amplitude spectrum for each of these stations on the surface. And the second point is in this case, as we want to see the level of noise and we want to characterize the level of noise on the surface, which is recorded by the stations, we use the power spectral density that I showed you before for each of these stations. And in this case, we can evaluate how and what type of earthquake or which magnitude will be seen by these stations, looking at the level of noise. And because these are the distributions of amplitude, we can also look at the percentiles, which are basically the level of noise that we want to simulate. In this case, if we want to simulate, for example, a noisy case, day or a quiet case, for example, in night or weekends, which the level of noise is lower. So by setting up the percentiles, we are able to see different level of noise and the ability of this network to detect earthquakes. And this is an example of how this is done essentially for each of the stations on the surface. So we have for example, we set a percentile, so a scenario, and for different levels of magnitude of the events. So, for example, in this case, from 2.8 to 0.8. So we calculate the amplitude spectrum at this station, and we compare the amplitude spectrum of the source to the level of noise that we recorded. So, and we show through the power spectral density. And we see that in the case of a strong earthquake, so in this case 2.8, this line, so the amplitude is of this earthquake is higher than the power spectral density, the PPSDs, and means that we are able to detect these events for up to 10 and more hertz. However, if we simulate in an earthquake with a lower magnitude, for example 1.8, we see that only, so the curve, the dashed red curve represents the amplitude spectrum of this source. We see that only for low level of noise, so we see that for a quiet scenario, we are able to see this event. And finally, for a magnitude of 0.8, the amplitude spectrum of that event is below the ambient seismic noise, so we cannot we are not able to detect it. So basically, we do this for each of these hypothetical hypocenters and for each of the seismic stations on the surface, and we can build up some network sensitivity maps, which indicates which is the minimum magnitude that can be detected by that network. And again, because we want to maximize the detectability of earthquakes, we want to reduce the minimum magnitude of the earthquake that can be detected. So we want to choose locations where the background noise is very low, but in case of very noisy areas, we can also use borehole stations where we can put station up to hundreds of meters in order to reduce quite strongly the surface noise. In that case, we are able to see even much lower earthquakes. So here I show the first case study that the importance of the location of, as I said, of a station. And this case study was done in France, where we put this is a subsection of a subset of stations on the main that I showed you before, the temporary network. A subset of stations which were deployed orthogonal to a road on the west side and orthogonal to a railway on the east side. And they deployed 11 nodes, and the conditions were ideal because they were in a wooded area, far away from industrial activities, cities, and so on. So we were able to isolate the contributions of the road noise and the railway noise. And these linear arrays were recording continuously for 20 days. And in this case, I show the differences in the signals for the stations close to the railway and close to the road, both in time and the frequency domain. And we see already from these figures, they are very different in time domain, where we see spiky characteristics on the railway. So basically, each of these spike is a passing train close to the station, and while the road is, on average, it seems to have much higher background noise, as we see, and the spikes are not very energetic like the trains. Of course, trains are the mass of trains are much higher than cars, so this of course influences the response of seismic response. And these signals can be also employed as active sources and to characterize the subsurface near the railway as active surface, active sources. If we see in a frequency domain, so we see different frequency bands from 2 to 20 hertz to these two stations, we see that the railway, again, also in the frequency domain, is very clear the spiky characteristics for the passing trains. However, the background noise remains pretty constant throughout the frequency bands. However, the road, we see that there is an excitation of the different frequencies, in this case 10 and 20 hertz. However, the 2 hertz remains pretty stable and very similar to the railway case. If we see the evolution of the PPSD from the, in this case, to the railway, up to the 1,000 meters from the railway, so the distance increases from left to right, we see that the amplitude distribution of noise is pretty low for all of these stations, but we see that there is a signal indicated by the arrows. These are the signature of the train passing the station. And we see that as we move away from the railway, we see that at higher frequency, the amplitude decays, and also decays even more energetically at 300 meters, and after 1,000 meters, we are not able to see any signature of this signal. If we compare it with road, again we see from here that there is a very more energetic seismic noise, but again we see this pattern that as we move away from the road, as we can expect, the level of noise decreases. But how this decreases as a function of frequency? So if we take the different frequency bands and we show the decay of amplitude noise, we see that for 2 Hertz there is no change. There is no decay with distance, so it remains pretty stable throughout the distance as a function of distance, both for the road and the railway. However, as we analyze higher frequencies, we see that the decay is exponential, and above 300 meters, beyond 300 meters, we see that it reaches a plateau, which means that the amplitude noise doesn't change after that distance. If we compare with the railway, we still see some decay, exponential decay, but because the amplitudes are much lower, in this case is not visible as the road case. But however, again, we see that beyond 300 meters, we reach a plateau. So to see the influence of this noise for station close to the road or away from the road, and how it influences the detectability of seismic networks, of seismic events, we just simulate 2 scenarios where we have 4 stations which are fixed in yellow triangles on the east, and 2. So we move 2 stations. In the first scenario, we put the station away from the road by 300 meters. In the second scenario, we move closer this station to the road, and we see how this influences the detectability of the seismic events. So in this case, as I showed you before how to calculate these maps, we are able to, in this configuration, we are able to locate and detect events up to -0.4 magnitude units. And again, this is reached within the seismic network. But if we move, so if we look at the second scenario, if we move just 1 station closer to the road, we see that there is a drop in the sensitivity, and there is a drop in the ability of this network to see some events, and we see that there is a drop of at least 0.2 magnitude units on the west side, just by moving 300 meters of 1 station in a network of 5. So this shows one of the key aspects of network design, where we want to avoid, as I said before, areas where the level of noise is high. And this is also important to show in general, and in this case to our client, that in different cases, when we want to deploy some network stations, we want to be at least a few hundred meters from the road. And so this is not the main highway, but this is a small road, and this is very so it's very clear the sign of this of the noise. And I showed the second case scenario. In this case, we moved to Switzerland, where we are from a survey design, so at the beginning of the study, to the monitoring results. And so essentially we are in Switzerland, close to the Genève Lake. And here the objective of the project was to extract water from aquifer, so where there is water up to 130 degrees Celsius. And there are some fractured networks which basically the water percolates in the subsurface, reaching the target point at around 300 meters below the surface, below the sea level, where the water reaches roughly 120-130 degrees. And the project was to build up this geothermal project. There is already one single well, which is a production well. What we did was to monitor the prey before the injection, during the injection, the production, and after the drilling, and to this geothermal deep well. And we also deployed 3 more stations, because at the beginning there were only 7 stations. We deployed 3 more stations to improve the azimuthal coverage at the center of the where the well was drilling. And so we optimized the position of these stations, and we also calculated, as I showed you before, the magnitude, so the sensitivity of this network, and the location uncertainties. As we see here, the sensitivity through simulations shows us that we are able to see, using this this network, we are up to -0.4 again of local magnitude that we are able to detect closer to the well. And of course, degrades outside, reaching -0.2 and more when we are at distance from the main stations. So this is the calculation and the estimation of the theoretical or horizontal and vertical location uncertainties, because we need to be below some thresholds that we have to provide to the client. We tested that using this network we are able to stay below those thresholds. The interesting things here is that after the monitoring, so in the monitoring phase, which lasts around 10 months, so from November 2021 to September 2022, we were able to detect 451 events that we show here in the map on the right-hand side. So each point is a seismic event. So there are some different clusters of events. So for example, these are quarry blasts. So in some quarries. Here on the bottom, there is a dam, which also can induce earthquake by the moving, the water which moves and can cause some induced events, and then some natural events which are originated by a known fault. So here are the main domains. What we see, we didn't detect any activity of seismic activity within the monitoring network domains. But interestingly, if we look at the magnitude that we were able to detect, was to on average is around 0.18 local magnitude as a unit. However, there are some events at -1, very small. But if we take the standard deviation of this distribution, we see that it goes from 0.4, roughly 0.4 to 0.8. But the minimum magnitude, if we take into account the standard deviation, was -0.4. So in our scenario that we simulated, the minimum magnitude which that network was able to detect was -0.4 within the network. In this case, we did it better. So we were able to detect even lower magnitudes. So in our case, as we try to do, is a slightly conservative. However, we picked very well the magnitude that we finally, in the monitoring result, we were able to pick. So at this point, I don't know, to be honest, how long I've been talking.
Hello, Antonio, it's Odile. So I arrived at 10. Hello, I'm sorry, I was not available before 10. So the schedule is to finish in 15 minutes or so.
Okay.
And then they have a break, and then we start with a doctoral presentation at 11. So roughly you've got, I don't know, maximum 15 minutes, because to have a question, a little question, and have a small break.
That's perfect, because at this moment I can give the floor to my colleague Sofia, who will show another case study in China related to this latest.
Okay, so maybe we will have the question at the end, but
yes.
Is it enough, Sofia, 15 minutes? Because it's going to be maybe frustrating, but I think we have.
No, it's okay. It's okay. Don't worry. I can do
okay,
I will try in 10 minutes, so I can give you the time to processing all the information that Antonio already gave to you, and maybe make some questions. So I will try to stay in 10 minutes.
Antonio and Sofia, don't forget to send your short bio to Fatima, so that we can post this on the web. Thank you very much.
Okay, thank you. So I will share my screen. Can you see it?
Yes.
Good. I will go on presentation mode. Can you see the presentation mode?
Yes.
Great. Okay. So thank you. As Antonio and Alessandro already said, my name is Sofia Bressan, and I'm a PhD student actually at the University of Padua. And today I would like to show you this example of the hot dry rock geothermal system in China. With this presentation, I would like to illustrate the importance to do these preliminary network design studies that Antonio already talked about before the actual acquisition of the data, because in this case study, they didn't. And I will show you how the data are effective by this important part of the study. So I actually performed some microseismic analysis in the area with a lot of university involved, and in particular the Chinese Academy of Geological Sciences that collected the data on the site. So, as I said, the project is located in China, in the northeast part of the Qinghai region. That I don't know if you can see, my mouth is here. And they start drilling in 2017, but they actually started the operation in 2019. And since that moment, the project has been considered one of the most promising hot dry rock system in China, because of the temperature of 236 degrees that they reach at 3.7 kilometers depth. That is quite low. But before everything, I would like to explain what is an hot dry rock system, because maybe a lot of you don't know it. So hot dry rock system are a specific type of enhanced geothermal system, and both of them are an advanced geothermal technology designed to create or enhance fractures in deep reservoirs by the injection of high pressure water. And in specific, hot dry rock are designed for hot, dry, and impermeable rock formation, where we don't have natural fluid circulation. So the idea of the injection of the water is to create this circulation of the water that we can also extract and use to create energy. So the main target is energy production. So here I wanted to show you what the seismic network look like. In specific, I want you to focus on the distribution of the geophones, because the area is pretty small. We are talking about a coverage area of only 2.5 kilometers square, and we have more than 20 stations in this area. So very small area and a lot of sensors in it. So a brief overview of the geological background, because I think it's very important to understand it. So here we have our site that is located in an area that is surrounded by two dominant lateral strike slip faults, that exactly represented by this small sketch here. And then we have other two dextral strike slip in the area that create more complexity in the geological stress field, plus two thrust faults that are those ones that are with specific cinematic. So you can imagine that this central block here is behave like a very huge, large-scale fault, and also is rotating anti-clockwise. So the complexity of the area is very peculiar, and the stress regime is defined as a compressional stress regime with this northeast-southwest orientation. Okay, so going through the microseismicity analysis that I perform, here we have a plan view of the, again, of the seismic network, and the 3D view, because I wanted to show you where the injection and the two production wells are located. But more specifically, I want you to focus on the seismicity. So during 4 months of operation, we collected more than 2,000 microseismic events, and we automatically located them. Then I went through the microseismic analysis, and I selected 204 events with the high magnitude values, and I decided to manually locate the events. So if you can see here, if I go back and forth, you can clearly observe a huge location discrepancy between the two methods, probably because, again, the sensors are very close to each other, which make the location very inaccurate. That's the reason why we decided to reprocessing the data, again, for the third time, using a different method called Table Difference method. That is a relocation algorithm that minimizes the travel time differences between two events detected by the same sensors. And these events are, we call it master and slave, and we compare the two events to each other in order to implement the localization occurrence. So as you can see from the image here, the yellow point represents my manual location, and the light blue event represents the location of the event after Table Difference method. So we can clearly see that all the events going through close to the injection well. That is exactly what we expect from this kind of project. Then I perform a shear weight splitting analysis in order to understand the orientation of the fractures that we have into the area. And shear weight splitting is essentially the separation of the S wave into its two orthogonal components when the S wave reaches the fractural material. So you have to imagine the S wave and the anisotropy in the materials, and the components that is parallel to this anisotropy will be a little bit faster than the other one that is perpendicular to it. So it also means that the first component will reach the sensor sooner, and we are able to study and to evaluate this arrival time delay and to define the orientation of the fractures. So in our case study, the fractures are clearly oriented in north-southwest direction that is consistent, as what I said before, with the regional stress regime that we have in the area. And this is very important for us because with the injection of the water, in this case, we are not creating new fractures, but we are activating fractures that were already present within the study area. Then I perform analysis of the waveforms. So I decided to extract the amplitude and the frequency value from the P waves and the S wave in order to define the window length, time length, to calculate and to perform a cross-correlation analysis. So cross-correlation is a very common technique in geophysics that help us to understand how similar two waveforms are to each other by sliding, as you can see here, sliding the trace one over the other in order to understand their similarity. And the resulting cross-correlation metrics help us to understand the similarities of the two waveforms that we are comparing. Using this cross-correlation matrix and in particular analyzing the dendrograms that come from this analysis, we are able to clusterize our waveforms, so our events, and we were able to detect 7 different clusters. 2 of which shown dominant consistent orientation with 2 dominant seismogenic structures that other authors already presented for the same area, but for different injection periods. This is very important because now we have a constraint of what kind of seismic sources are the main source for our events. So we decided to focus on these 2 clusters and we perform principal component analysis in order to extract the fault plane surfaces. And in particular, we want to extract the parameters of these surfaces, so the strike and deep and the rakes that are all the parameters that characterize the fault plane, and use these parameters to modeling the propagation of the event. So here I wanted to show an example of one of the results that we obtained. So we have this small event in the blue cluster here. I also reported the original waveforms just because I want you to focus on the fact that we didn't perform any analysis on the noise level because, as you can see, the background noise here is pretty low. So we didn't perform any analysis of this kind of things. And then we passed on the analysis of the waveforms and the analysis of the modeling. So here on the right, you have again, the seismic network, and this line here represents the view of the modeling, the seismic propagation modeling that you have in the left. So on the surface, we have the sensors, and at 3.7 kilometers up, we have the hypocenter of our selected event. And when we start the analysis, we can clearly see the propagation of the P wave and then S wave. And as soon as the P wave reaches the surface, the sensor will collect and detect polarity. Those polarities are negative for 3 out of 4 of our sensors, and then we compare that information with the real observed polarities on the surface, and we can clearly see that we are on the right direction for this kind of analysis. But the main problem here is that 4 sensors are not enough to constrain the focal mechanism, to constrain the polarities, and most important, to constrain the fault planes that is the seismic sources of this event. So what we can clearly see and say from this information is that all of the analyses are performed in a negative way due to the fact that the seismic network is pretty small. Because according to the guidelines for the analysis of 3 and 4 kilometers depth, we must need a coverage area in the surface that is at least the double. So we are talking about 8 kilometer square area, not 2.5 like our case study. That's the reason why we decided to redesign the network to perform a better localization of the analysis. And that's the reason why this kind of analyses are very important in a preliminary stage, because when the analysis already have performed, you can clearly see that they are negative affected by the coverage area. So that's just what we observe from this thing. So that's it. I think I stay in the 10 minutes. I hope so.
Okay, yes. Thank you very much, Sofia. If you agree,